So we are going to talk about the EM algorithm now. That is basically the expectation maximization algorithm. Okay. So in that one, we are going to talk about what is the EM algorithm basically. EM algorithm, and the formal definition that we should say is the expectation maximization algorithm is an iterative optimization method. Okay, just remember this thing. Iterative optimization method for finding the maximum likelihood estimate MLE or maximum a posteriori MAP estimates when the data is incomplete, means some values are missing. They are latent or hidden variables that are not directly observed, and the likelihood is intractable to maximize directly. All right. So these are the things when we use the AM algorithm. So this method was given by the Dempster, Laird, and Rubin in 1997. That was published in Royal Statistical Society Series B. Okay, and the this is the one of the most important method for the analyzing the data in statistics, because in the statistics we rarely have the complete data set. We mostly have the incomplete data set, and we do not have the complete information about the given data set. So at that time it becomes very difficult to find out the estimates and forecast. So that time EM algorithm becomes very important in study. Okay, so that's why if you just see the citation, what happened. Okay, that is citation more than 90,000 times. Okay, means this algorithm is that much important, and it is also as well as the difficult to apply. That if you just apply EM algorithm in your research paper, it will simply publish, okay, by any journal, and very in a very easy way. They will not ask you the so many questions if you mention the EM algorithm, or you just apply the EM algorithm in your research papers. They will very easily accept your research paper. They will not ask so many questions, because it is not easy task to apply the EM algorithm. Most of the people are not in the even the statisticians more are not able to apply the EM algorithm directly. Okay, especially the coding, they are not able to apply that one. So what is the EM algorithm in the two-step iterative method? So what you have basically, you just start, you have the incomplete data set here, incomplete data set, and you just start with that, and you find out the estimate of the parameter that you are going to denote by theta naught. Okay, after that in each step you compute the expected complete data log likelihood. All right, with respect to the conditional distribution of the latent variable, say z. Okay, z is your latent variable. With respect to that, you just find out the expected value of the given data, and for the given object data set, and current parameter theta t. So you find out the theta t at that time, and then we define a function q, that is basically the expectation. All right, and this is step accounts for the uncertainty in the latent variable. After that, this qt we define here, that qt is basically, if I just say qt, q theta given theta t is basically defined as the expected value of z, that is your latent variable given t, for sorry for x comma theta t is log of likelihood function, that is say f x comma z given theta. That is the expectation of that one. All right. So with the this function q theta given theta t, we just this m step function, that is finds the new parameter called theta t plus 1. Okay, t plus 1 that maximize the theta, like in such a way that basically theta t plus 1 is equals to argument of maximum theta q theta given theta t. Okay, that is going to maximize that one, because the complete data model, that is your f x z given theta, is often choose for this mathematical convenience. For example, from the exponential family, this maximization is usually straightforward and can often be done in the closed form. Okay. After that, we just check, after maximize this one, we check the convergence. Okay. In the next step. So this is the very important property of the EM algorithm, is that means in each iteration we just check that it is not decrease the observed data likelihood. Okay, it should increase only, means in every iteration likelihood of for the given parameter theta t plus 1 for the given x, okay, that should be greater than equals to the likelihood of parameter theta t for the given x. All right, with equality only at a stationary point, or often we call it the local maximum. Okay, this is this is proven by using the Jensen's inequality and construction of the Q function. Okay, I hope you know the Jensen's equality, right? That is, do you know about the Jensen's inequality? Do you know about the Jensen's inequality? Okay. So what is the Jensen's inequality? It basically, it says that expected expected value of gx function of gx is the function of x is greater than equals to function g of expected value of x. Okay, so that is the Jensen's inequality. Means if you just going to take the expectation of the function of x, it will be greater than the expectation of x over the function of that of the x. Okay, so that is called as the Jensen's inequality. Means basically what we say from the variance. If we just take the example of variance, what is the formula of variance of x in the expectation? Expected value of x square minus expected value of x whole square. Yes or no? This is the function. This is the formula of variance of x. Right. So now everybody knows that variance is greater than or equals to 0. It cannot be negative. If we are going to take this inequality, so what we will get, expected value of x square is greater than equals to expected value of x whole square. Means here, what is the gx? Gx is x square. Okay, square of the x. So if you just compare both of them, this one. So you will find that, sorry, this. So you will find that expected value of gx, expected value of x square is greater than equals to the square of expected value of x. Right? So that is called as the Jensen's inequality. So we are following this one here. So next time when you are going to generate the theta t plus 1 from the theta t, it will be greater than equals to the likelihood of L theta t plus 1 will be greater than equals to L theta t from the previous value. So this should happen, and it should, after the when you are going to repeat it, so it should converge. If it is not going to be converged, so what you will do again, if it is not going to be converged, so what you will do, you will go again and you will find out the expectation again and then try to maximize, and again you will check the convergence. If it is going to be converged, so that will be your theta cap, your output. Otherwise again you need to go and you need to find out the expectation, and then again you need to find out the that one, maximization. Okay, so that is the core idea of likelihood. Okay, the core idea of the likelihood EML algorithm is that when direct maximization of the of the likelihood is difficult due to the missing data or latent variables, okay, EM circumvent the problem by filling in the missing data by expected values or maximizing is as if the data were complete. Okay, and repeating it until the convergence. Okay, so here I forget to tell you that about the latent variables, how they are going to impact. Okay, uh, do you have the idea about the latent variables study? Do you have the idea about the latent variables study? Okay, so what happened? Suppose few patients have the fever. We are taking the very simple example. Few patients have the fever and they are going for a treatment to a doctor. And at the time when doctor provide the prescription or the medicine, what usually doctor check? Doctor check the temperature of the body. That is your that will for your fever. Okay, that is your study variable. And after that, what he basically check? He check the weight. Then he asked basically the age, and then check the gender. Okay, these are the things. And another thing that he asked what people are eating. These are the things that doctor check. Yes or no? Eating habit. These are the only things mostly when doctor is going for the treatment for the fever patients. That only he asked. Yes or no? Most of the time, right? But tell me one thing, and these are the things that you can observe. Okay, these are the things that doctor can observe. So this will be called as the observed variables. Okay. Now just a thing. Only these are the variables that are going to impact my body or my temperature. What about the weather and the environment outside? Maybe environment is not suitable for my body. Yes or no? It is possible that environment is not suitable for my body. And second thing is that if I am, and how many hours I am sleeping, that is the one thing. But when I am going to sleep, I am sleeping at 9 p.m. Okay, or I am sleeping at 1 a.m. or suppose say 3 a.m. I am sleeping at 3 a.m. And doctor, I am telling that doctor that I am taking 7 hours sleep. Okay. Have you ever noticed that when you are taking the sleep from 9 p.m. and when you are taking you are going for the bed at 3 a.m., even though after the 7 hours of sleep, there is a difference. You feel the difference in your body, or you feel the some kind of difference in your activity or activeness. You feel little bit tired when you are sleeping at 3 a.m. Even though after you are going to wake up at after 7 hours, you feel some tiredness. Yes or no? Do you feel some tiredness even though after taking the 7 hours sleep? Most of the time it happens. Okay. So what about the effect of that one? Can I measure the effect of the this one? That how I will measure this difference? That because doctor knows that I'm sleeping for 7 hours, but he doesn't know that at what time I'm sleeping and the weather outside. It is good for my body or not. I can feel it, but how will I measure it? I cannot measure that these things or genetic structure of my body. Nobody can measure that one, but that will play a important role when I'm going for the treatment. Yes or no? Right? It will play the important role. So these variables, like the impact of the environment, okay, environment, sleeping time, these are called as the latent variable or unobserved variable that have the impact. So in some study like the linear regression model, what we do, we just put these variables in the error epsilon. When you just study the y equals to x1 beta 1 plus x2 beta 2 plus up to xp beta p plus beta naught is also there. Okay, so beta naught plus epsilon. Okay, so what I do in the usually in the study, I put these variables in the error. We just transfer them in the error, but I cannot transfer them in the error. I have to check that what they are going to means either they have the impact or not. So there are several studies or several methods. One of the method is that we call it as the frailty models. Okay, in that one we incorporate the unknown covariates here. So we just want to check those impacts, and that how we will check them, we will check them through the EM algorithm. Okay, so that is the basically idea of the central idea of EM algorithm. And why does it works? The complete data log likelihood is often easy to maximize, but we cannot maximize the likelihood with the incomplete data set, and we can compute the expected complete data log likelihood. Okay, and maximizing this expectation guarantees that the observed likelihood is increases. So the key guarantee is that one that I told you, that likelihood for theta t plus 1 will greater than equals to likelihood of at the theta t for every iteration t. Okay, so it will increase every single time. Okay, so likelihood never decreases till it is not going to be the stationary state. Okay, so type of the data problems addressed by the EM algorithm. So in that one, the first one is the missing data. So survey responses with the unanswered question or medical records with missing lab values. All right, and the sensor data with dropped readings. So these are the this is the missing data possibilities are there, and the latent and hidden variables, cluster membership in the mixture model, hidden state in the hidden Markov models, unobserved ability in the psychometric models. Okay, and other one that I gave you here for the fever. example, and censored and the truncated data set. So survival times with the right censoring, detection limits in environmental measurements, and income data truncated at the reporting thresholds. So these are the some errors, some type of data problems that algorithm handles. Okay, so in that one, situation where EM is essential. So when standard MLE fails, so direct MLE, what is the MLE basically? Log likelihood function of our given PDF or PMF. Okay, this will be intractable because the integral or sum over all possible hidden values is complex and high dimension. Okay, do you know about the PMF or PDF for sensor data? How we observe the PDF or PMF or likelihood for the sensor data set? Do you have any idea about that one? Give me a second. So see, this is the way of constructing the likelihood function for the sensor data. So this is the likelihood under the right sensor. So where what we have fxi theta, this is the PDF of our study variable, and we are going to take the power raised to the power delta I for the uncensored data, means whatever the computed value I will keep here, and for the remaining value that are censored, for them I am going to put the survival function instead of the uh, PDF. Okay, then I compute the likelihood function. Okay, for further study. So what happens most of the times, if the distribution function is complex or number of parameters are very high, at that time this likelihood function becomes very difficult to compute or to maximize. Okay, by some um, classical methods like MLE and other things. So at that time, what we do, we just go for the EM algorithm at that time. All right. So because what happened, the resulting function is most of the times is the non-convex. All right, and the taking derivative leads to the complicated expression, because if you are going to, if you just see how we find out the MLE, we find out the MLE with respect to the, when we find out the derivative with respect to the parameter of log likelihood function, and we put it equals to 0, and suppose here we have the gamma function. So the survival function of the gamma distribution is not in the closed form, right? And the PDF is also there. And when you find out the MLE with respect to the parameter beta, so what happened? At that time, you find out, you get the derivative of, see, derivative of gamma function, gamma beta. Yes or no? Do you know the MLE of the likelihood function, gamma function? Do you know about the likelihood of the gamma function? Okay. So in that one, when you find out the likelihood of the gamma function, you always find that you have the gamma beta and derivative of gamma beta, and that you cannot find out in the closed form. And after that, you have the survival function. What is the survival function? That is the uh, t to infinity of your PDF of gamma function. Okay, that is not in the closed form at all. So how you will find out the MLE here? How you will maximize it? It will becomes very difficult. So that's why we need the EM algorithm at that time. All right. So when we should use the EM algorithm, complete data likelihood has a simple form. E step means expectation are tractable, means we are able to find out the expectation of that function, and M function has the closed form solution. If M function is not have the closed form solution, so at that time it will becomes very difficult to apply the EM algorithm. All right. So it should be in the closed form, and the numerical stability is important. Means when you are going to go for the uh, iteration, so monotonic increase property should be apply here. All right. If it is not going to be applied, then becomes very difficult at that time. So some real life examples are there for the application of the EM algorithm. So first is the genomics and bio from the bio and bioinformatics. So in that one, we have the expression analysis. The in the microarray or RNA sequence data with the missing values due to the technical issue. So EM can be imputes these values by exploiting the correlation structure. Basically, a missing data problem that will be, and the sequence elements are there. The second one, the hidden Markov model for DNA and protein sequences. So in that one, the latent variables are the match or insert or the delete states. So there is a one algorithm that is called as the uh, B Baum and Welch algorithm. Okay, so this algorithm learns the model's parameter at that time, and another one is the population genetics. So EM estimating the allele frequencies with incomplete genotypes. So that untyped uh, markers are the missing data. So EM inputs those missing genotypes and estimate the haplotypes frequencies here. And another example from the clinical research. So in that one, survival analysis. So censored patient survival times is there. So the true unobserved survival time is the latent variable, and EM fits the parametric survival models. Another one is the diagnostic testing. So estimating the disease, okay, prevalence without a gold standard. So the true disease status is a latent variable. Okay, so EM jointly estimate the prevalence and the test characteristics here. And third one is the missing clinical data. That is basically the lab values or follow-up measurements missing at random. So in that one, EM algorithm provides the principal imputation under the MAR assumption. Okay, and that one, after that, we have the examples that I gave you for the CT reconstruction and brain MRI segments. All right, that are the examples of those real life situation, and some examples I just gave here for the industry and technology. So finance and economics. So in that one, credit scoring. So customer data with missing fields. So like incomes. So EM inputs the missing values before model building. And another one is the portfolio optimization, returns with the Nocracious trading. So this creates the missing data platform. EM algorithm or EM estimates the it build the covariance matrix of the returns, and regime and switching models are there. So here uh, in that one, hidden market states. So in that one, we call it two types are there, bull and bear. So this is an HMM models, that is called as the hidden market states models. So in that one, the latent variables is the market regime. So EM algorithm basically estimate the transition probabilities and regime parameters here. Okay. For that one, I just give you the examples. And now I have some examples from the natural and social sciences. All right. So now we just come here for the fundamental problem with incomplete data. Okay. So suppose here complete versus incomplete data. So complete data, we observe everything we need, that is x1, x2, xn, and it will follow some distribution here fx theta. And incomplete data, we only observe the part of that this particular data. So observed data will be y, that we can see here, and the missing data or the latent data is the z, what is hidden, that we do not have, and both of them of combiningly prepare a complete data set, that is we call as X. So basically, what is there? We have the random sample X, X1, X2, Xn, okay, drawn from particular distribution F with parameter theta, and the likelihood function L theta given X, okay, has known and tractable. From that we can maximize the directly, and in that one, after that, what we are going to do, uh, but in the reality, what happens? We do not have the completely observed data. We just divide the data into two parts: complete data and the unobserved data set. So observed data is basically that we have in the Y, that is called as the complete data set, and another one is the part, that is Z, that is basically we cannot compute properly. We have only the some observation about that. So this can be physically missing or structurally latent or censored or truncated. All right. So that after that we compute the complete data hypothetical. This is basically the hypothetical construction of the data. So because we have only observed value y, and we must work on with the observed data set. Okay. So at that time, the observed data likelihood function will becomes L observed theta for the given y is equals to the integral or the summation of the likelihood of the computed theta y z with respect to the dz, and that will be equals to integral f y z given theta dz. So this integral is the source of the difficulty. So it is very difficult to find out because of the high dimension and lacking of the closed form solution. So here we will not find the closed form of the likelihood most of the time. And if the number of parameters are more, so we need to integrate more number of times. So what they have done, so missing data mechanism. So Rubin's classification is there. MCAR, missing completely at random. That is the one classification of the data set they had. Means probability of the missingness is independent of all data set. For example, the random equipment failure is there. Okay, so what is the definition that he provided here? MCAR, missing completely at random. Okay, the definition of this is basically the probability of missingness is independent of both the observed data and the missing data. Means the probability of missingness, sorry, not missingness, the probability of missing, yes, yes, missingness is independent of is independent of both the observed data and observed data, say y observed, and the missing data y missing. Okay, means probability, mathematically the probability that are, okay, the missingness, given that we have the y observed and y missing for the phi, is equals to the probability of r given phi. Alright, so for example, is here the random equipment of the failures means the observed data is simple random subsample of the complete data, and complete case analysis is unbiased through the inefficient. Okay, so it will be inefficient, so we will use that one. And another one is that MAR, missing at random. Okay, so that is basically MAR definition will be the probability of missingness, the probability of missingness depends only on the depends only on the observed data. Sorry, observed data. Okay, y observed and not on the missing data, and not on the missing data. Sorry, y missing given the observed data set. Given the observed data. So what is it mathematically? The probability that r y observed is and y missing for phi is equals to probability of r given y observed and phi. All right. So in that one, the example is that older patients means observed age are more likely to skip the survey questions. All right. So missingness depends on the observed age, not on the missing answers. All right. So how we are going to apply this? MAR is the standard assumption for the most maximum likelihood based missing data methods, including the EM and the multiple imputation. So the missingness mechanism is ignorable for the likelihood based inference. So we maximize the likelihood of theta for the observed value without modeling the PR given observed phi. All right, provided that the theta and the phi are different things. All right. So then after that MMAR we have, so missing node at random. So in that one, what is the definition of this one? MNAR. Okay, so that is basically probability of missingness depends on the missing data. Probability of missingness depends on the missing data. Why missing itself? Even after accounting for the observed data. Even after accounting observed data. Why observed? All right. So that is basically probability of R given Y observed and Y missing for the 5. Right. So in that one example is that high income individuals systematically refuse to report their income. So the missingness is directly related to the unobserved value. So MNAR is the most challenging scenario. So in that scenario, the missingness mechanism is non-ignorable. To obtain this valid inferences, one must explicitly the model, the joint distribution of the data, and the missingness mechanism. So in that, the standard EM algorithm at presented is not appropriate without significant modification. So we need to do some modification in the EM algorithm to apply the MNAR model. Missing not at random. So EM algorithm typically assume MAR and MCAR. So for MNAR, the missingness mechanism must be modeled explicitly. So now we just take the one real life example, not real life. We just take the example. That is the classical example of the EM algorithm that we have. So here, what we are going to do, we have the scenario is that we have two coins, say A and B, with unknown bias probabilities, that is theta A and theta B. And the experiment consists that the randomly select one of these two coins, each with probability 0.5, we are going to select, and we are going to flip the coin 10 times. We are going to flip this coin 10 times and record the number of heads. So in that one, the problem is that you lose to track of which coin was used. Suppose we just pick the two coins were there, A and B, and we pick the coin at random and we just toss the coin 10 times. N equals to 10. 10 times I'm going to toss that one. At that time, in the last, I don't know, whatever the number of heads comes. Suppose 5 heads comes. So I don't know out of these 5, how many heads comes from the first coin and how many heads comes from the second coin, say B. So I don't know that one. So how will I will find out that what is the probability of theta, what is the value of the theta A and theta B? What is the probabilities from the that head occurs from the theta A or means coin A or coin B? How I will find out that one? So we observe the outcomes head and tail, but not which coin was produced them. So the coin identity is the latent variable here. Right? Are you getting that one? Are you understanding this example? What I'm trying to say here? Okay. So now thing is that we repeat this experiment 5 times, 10 flips at each, and in first experiment I got the 5 head 5 tail. In second experiment I got the 9 head 1 tail. In third experiment I got the 8 head 2 tails. And fourth experiment I got the 4 head and 6 tails. And the fifth experiment I got the 7 head and 3 tails. So what we know here, we know about the outputs. What are the outputs that we have? Okay, we only observe the number of heads here, okay, and number of tails. What we do not know which coin was used for which experiment. Okay, so we don't know in each trial or in each experiment which coin we have used, either A or B. Okay, so that in that one Z is the latent variable. So our goal is to find out the estimate value of theta A and theta B, the probability of heads for each coin. Okay. So now thing is that why can't we use the standard MLE here? So what if we knew which coin was used? So in suppose that I know that for the experiment 1 4 I used coin A. And for experiment 2, 3, and 5, I use the coin B. So at that time, it is very easy to find out the estimated value. So what it will be at that time? The number of heads occur in first experiment 5, and how many heads occurs in the fourth one, that is 4. So 5 plus 4 divided by total observation was 10. So 10 plus 10, 20, 9 above 9 divided by 20, that is 0.45. And for the MLE, it will be what it will be 9 8 plus 7 divided by 30, so 24 divided by 30, so that will be 80. So what is the problem occurs here? We don't know the coins assignment, means we don't know the likelihood involves the summing over all possible assignments. So computationally probative and the analytically intractable, means what is happening here. Here we don't know what is the assignments, means which experiment has the which coin. So what is our basically that one likelihood function here. Okay, so in that case the observed data likelihood involving the summing overall observation, means how many total assignments are possible here. Okay, how many possibilities are there in this one? Only two coins are there. Each coin we have used 5 times. Okay. So whatever the total possibilities, 2 raised to the power 5, that is 32. 32 possibilities are there. Okay, possible assignments. So in that case, the likelihood, what will be the likelihood? The likelihood will be likelihood theta A, theta B, the combined joint likelihood for the given data set. It will be equals to the likelihood, the product of over the range of I goes to 1 to 5. Okay, raised to the power, sorry, into 1 by 2 into tan chi. Okay, theta raised to the power hi for A, and 1 minus theta raised to the power, sorry, theta A raised to the power tan minus hi. Okay, plus, because half is the probability to select one coin. So that's why we are multiplying with the probability that selecting the one coin here. So selecting the probability of selecting the another coin, that is 1 by 2. So 10, the hi means which experiment we are taking. The 5 experiments are there. Okay, and theta raised to the power theta b raised to the power hi and into 1 minus theta b raised to the power 10 minus hi, which head is occurring. Okay, so maximizing this directly is very difficult. This is the likelihood function that we have. If you are going to maximize this one, it is very difficult to find out because hi is changing, means number of heads is changing in every single experiment here. Okay, so what we will do, we will use the EM algorithm iterative method here. So what we are going to do now, the overview of the likelihood. So iterate between two steps. Okay, E step, that is having the, for the given current estimates of theta AT and theta BT, we will compute the probability. Okay, that experiment I use the coin A, that will be, what will the probability at that time here? We said gamma IA, means in the ith experiment we use the coin A, that will be the probability that coin A was used, coin A was used for, with the given, for a given heads hi and computed value of theta A and theta B at tth iteration. Okay, that will be your gamma I, and in that one, after that we will update the parameter in the mth step for the given the expected assignment for each step, and update the theta A theta B to maximize the expected complete data likelihood. Okay, so what we are going to do after that, we are going to find out in the next step. So this is our E step. In the M step, what we are going to do, we will update the parameters by using weighted average. Weighted average. So what will be those averages? Those averages will be theta A t plus 1 equals to summation over the range of I goes to 1 to 10. Okay, and gamma I, sorry, I equals to 1 to 5 because 5 experiments are there. Gamma A into Hi divided by summation over the range of I, gamma I A into 10, because total number of heads are, uh, total number of head or tail will occur, that will be 10, and theta B t plus 1 will be equals to summation over the range of I theta, sorry, not theta, gamma I B Hi divided by summation over the range of I gamma I B into 10. Okay, so where gamma, sorry, gamma I B is equals to 1 minus gamma I A. Okay, so means gamma is basically the probability that we are going to choose the coin A, and gamma B is the probability that we are going to choose the coin B here. Okay, and then we will repeat it each. step and the m step until the convergence. Okay, so other things we will do in the next class. Okay, these all things we will solve in the next class. All right, and I think okay, just give me a second.